Now to the next oral communication, we have Leonardo Furuta, who is a PhD student here at the graduate program of physics at the Federal University of Pará. Leonardo today is going to talk to us about massless scalar absorption by dirty black holes. Please, Leonardo, go ahead.
Can you hear me? Okay. Thank you, Luis, for the nice introduction. So my name is Leonardo Kenji do Santos Furuta, and I'm going to talk about massless scalar absorption by dirty wormholes. So this work was done in collaboration with Renan Magalhães, Haroldo Lima Jr., and the Professor Crispino. This is the outline of my presentation. In the first section, I give introduction and a motivation for this study. In the next section, I will give the description for the geometry of the dirty wormhole that I used in this work. In the third section, I studied the massless scalar field. I calculate the quasi-bound states and the absorption. The next section is our conclusions and the reference. So wormholes are space-time with a Furuta-like structure that can connect two different regions of two different universe, as represented in Figure 1, or they can be connected to different regions of the same universe, as represented in Figure 2. And one of the main reasons for study wormholes is that can mimic some of the black hole phenomena. So in the Figure 3, we have the comparison of the gravitational wave form emitted from a radially falling test particle into a wormhole and a black hole. So if we see attentionally the early signal is very similar, but the late time the late signal is different. So the wormhole can mimic the black hole signal at the early time. And we know that the astrophysical black hole have matter around them in the form of accretion disks or jets of matter, and we expected that this matter can influence some of the black hole phenomena. But we saw in the last slide the wormholes can mimic some of these phenomena, and then it's natural that we argue what would happen if the central object were a wormhole instead a black hole. So this is the main motivation for this work. To compute this possible influence of the matter around a wormhole, we use a toy model of a thin shell wormhole surrounded by a thick shell of matter, and calculate the absorption of the scalar field by this object. So we begin with the thin shell formalism. We use this formalism to glue two different spacetimes in order to produce a wormhole. So in the Figure 5, we have the standard configuration for the space-time gluing. We have two spacetimes, m plus and m minus. That in your case will be two copies of the Schwarzschild spacetimes. That line element is given in 1, where these r plus minus are the radial coordinates in m minus and n plus and n minus, and we match these two spacetimes at the same hypersurface sigma, and this sigma will be the wormhole float. So to add the dirtiness for this spacetime, we modify the wormhole line element as given by the equation 2, where this mass function m of r plus depends on the model of the thick shell that you are adopting, and we chose the model given n3, that is a piecewise function with this capital R function given in the equation 4, where this Rs, delta Rs, and delta M are the radius, the thickness, and the mass of the fixed shell. And for future computations, it's useful to define a radial global coordinate that can be used in the entire wormhole spacetime, and is defined implicitly by the equation 5, where this positive and negative sign describe the upper and lower side of the wormhole throat. So now we study the massless scalar field in this geometry. On each side of the throat, we have a Klein-Gordon equation given 6, where these plus and minus are again indicates the size of the throat, and we assume that the scalar field and its first derivative are continuous across the fin shell, so they are continuous across the throat, and they satisfy the equation 7 and 8, where this bracket notation denotes the discontinuity of the quantity. So we can separate the scalar function as given by equation 9, and using this equation in the Klein-Gordon's equation, we obtain a differential equation for the radial part of the scalar field as given in 10, where this V plus and minus is the effective potential for the scalar field, and we can also write the equation 10 in terms of the radial global coordinate that we defined earlier, and we obtain a Schrödinger-like equation given in 12. Now we plot this effective potential in terms of the global radial coordinate. We see that we plot the potential in terms of the global coordinates for several values of the multiple number and 2 configurations. In left we have a positive matter configuration, and in right we have a negative or a phantom matter configuration. We see that this potential has several streaming points, but in this presentation we are more interested in the minimum stable points, because if we have a scalar wave in this potential, this wave can be trapped in the potential minimum of the associated with this can be trapped in the potential well associated with these minimum points, and to calculate this trapped frequency, as known as quasi-bound state, we have to solve the Schrödinger-like equation, the equation 12. That is a eigenvalue problem with the boundary conditions given in 13. These boundary conditions represent poorly outgoing scalar waves at the both sides of the dirty wormhole spacetime at the infinities. And to calculate these frequencies, we employ the direct integration method. We calculate these frequencies and show it at the table 1. In left we have the frequencies for the phantom matter configurations. In right we have the ordinary matter configuration. We see that these frequencies are the real parts of these frequencies are similar, but the complex parts are different. And we see that for sufficient massive ordinary matter configurations, so positive matter configurations of the fixed shell, we can obtain additional trapped frequencies, and these additional trapped frequencies are trapped in the potential well associated with the fixed shell. we studied the absorption cross-section of the massless scalar function. So we have to solve again the Schoenlich equation, but now using the scattering boundary conditions given in 14. This boundary condition represents a monochromatic plane wave coming from the infinity of the M plus spacetime. Some part is being partially reflected back to the infinity of the M plus spacetime, and being partially transmitted to the infinity of the M minus spacetime. And to compute to calculate the absorption cross-section, we use the equation 15, where this normal square of the T omega L is the transmission coefficient of the scalar wave. So now we show the absorption of the scalar field for several values of the matter of the fiction. In left we have positive matter, and in right we have the phantom matter configurations. We see that the absorption has several narrow peaks, and each of these peaks has a quasi-bond frequency associated to it, and that are trapped in the wormhole throat minimum stable. And we see that for the absorption, the absorption cross section doesn't change much if we vary the matter of the fiction. Sorry, and but for sufficient massive configurations of the fiction, an additional resonance peak can be obtained at the low frequency regime, and we calculate this. We could calculate the quasi-bond frequency associated to this new peak, and we show it at the table 1. So this is my conclusions of this work. So we studied the thin shell wormholes surrounded by a thick shell of matter. We see that for large values of the thick shell matter, new quasi-bond states can arise due to the potential of the thick shell. And the most important conclusions is that the position of most of the spectral lines in the absorption bands is preserved. So this indicates that the thick shell cannot hide some of these fingerprints of the wormhole. So and this is my reference and my acknowledgements. Thank you for your attention.
Well, any comments, any question?
Hi, Kenji, and thank you for your talk. So you start motivating your work by saying that wormholes could be black hole mimickers, right? However, in the slide that you showed the absorption spectra, the absorption spectra for wormhole is quite different from a black hole. So do you think there is some range where they could be similar? I don't know, by increasing the frequencies or something like that?
So okay, the absorption of the wormholes are very different from in comparison with the black holes, but they can be very similar if we because this has this pattern because the radius of the throat is very small, so it's very similar with the radius, the Schwarzschild radius. if you chose a radius near to the 3m, that is the photon sphere radius, this do you don't have two peaks to one? Do you have one peak? So the absorption is very tends to the black hole pattern.
Any further question? Mark.
So thank you for your talk. So in general, when we compute the total absorption cross-section, we also try to compare our numerical results with some analytical approximations. So my question is, have you guys tried to find the analytical approximations for the total absorption cross-section in the low and high frequency regime? And if not, have you considered to use another numerical method to check the consistency of the results?
Okay. So for this wormhole, the high frequency regime tends to the Schwarzschild, to the shadow of the Schwarzschild black hole. For the low frequency limit, is an open question in the absorption for wormholes. I don't know if they are work in this topic, and we don't try other method to compare, unfortunately. Yeah. Also, for the phantom matter, for the phantom matter case, for sufficient massive, sufficient negative matter values, the high frequency limit is different from the Schwarzschild shadow, because for these values, the dominant light ring changes, and the shadow is smaller.
Okay.
Only.
Okay, thank you. Can I add something, or I don't know that?
Thank you. So let's thank Leonardo again.